Well, maybe I'll use the whiteboard. I always like it to be in our notes. Okay, so brace yourselves, all right? I could tell from the looks on people's face this was not fun. So the problem is it's a lot of concept, and we're not going to get to apply any of it today. Sometimes I feel like when I try to explain things and I don't use numbers, it doesn't make a lot of sense. Maybe I'll throw in some fake numbers in there to hopefully make it make more sense, okay? So we need to start talking about energy changes that occur in chemical reactions. If you just took Chem 1, you'll remember that you actually did a lab using the idea of heat and enthalpy in first semester. We just didn't cover that chapter, okay? You always have to cut something, and that's what got cut. So we're going to talk about the background information for that now. So hopefully, if anything, that will have given you a bit of an introduction to this, and it won't feel totally out of the blue. But we need to talk about it in a little bit more detail. So the first half will be, not even the first half, just mostly today will be concept stuff that give us the background information so that we can actually go and apply the concepts. But we just need to kind of like define some things today. So hopefully it's not too painful. Let me start by giving you kind of an overview of what we're doing, why we care about this. So when we look at chemical reactions, obviously we start with some reactants. And the example I thought of most recently was like a butane lighter, okay? So you have butane is C4H10. And when you flick the lighter, it releases some of the butane, reacts with the oxygen in the air, and produces CO2 and water. Okay? You also feel heat come off, right? That's why there's a flame. There is some heat coming off, some energy. So what that tells us about the chemical reaction is that the reactants must, and I'm going to draw this even more dramatically. Let's push these guys up top. The reactants must have been higher in potential energy than were the products. Because if heat came off, that must mean some energy was released in the process of turning the butane and oxygen into the CO2 and water. And there's a bunch of different ways that we can represent that. So let's just say the fact that we felt heat coming off of that told us that energy was being released. It was energy in the form of heat. Was released or given off is another way we can talk about that. I'm sure I'll think of another term. Okay, so that heat came from a difference in potential energy, or in what we're going to call internal energy in a second, from the reactants to the products. Okay, so I'm going to draw this like an energy diagram. Now, what this should look like is the best analogy that we know so far is when we talked about electrons. And we said electrons can be at a high energy state and they can jump down to a low energy state. Okay, so high potential energy, and then they can get closer to the nucleus at a low potential energy. Well, when that process occurs, if you remember, a photon has to be released. Light, okay? That's because anytime you have a change in energy, that energy has to go somewhere. So this is going to be on probably the second slide, I think, where we say the first law of thermodynamics is that energy can't be created or destroyed. It has to go somewhere. So if if this is my chunk of energy, okay, and I'm the chemical reaction, and I give it off, so this is heat, and you feel the heat, right? That came from me. It didn't just appear. It came from me. I gave it away, and now you, as part of the surroundings that are feeling it, feel that heat being given off, okay? So the way that we represent that in chemistry is to show It was at a high energy state. It went to a lower energy state, and that energy left, that chunk of energy. So like in the case of an electron, it was that much energy that was then given off as a photon. In the case of a chemical reaction, the way I have it drawn here, it's this chunk of energy, and that is actually given off very commonly as heat. So I'm going to show that leaving the chemical reaction. Okay? Now, it's not always heat. In this particular example, it is. But there are some reactions where it's a different type of energy. We're doing the test. Yeah. Yes. Where am I going to put you? Okay, just hang out there for a second, and I'm going to find a break point and take you upstairs. Okay, so when we have some amount of energy coming off, we're going to describe this a few different ways, and I'm not going to be able to think clearly until I go get him started on the exam. So what do I want you to do in the meantime? This is what I want you to do. Okay, so flip to this slide, and this is going to represent our chemical reaction. Okay, this is going to be the initial state, like think of the reactants, and this is going to be our final state or the products. Okay, and then this is going to represent everything else other than the chemical reaction. We call it the surroundings. And I want you to just make it make sense to you where that energy is going, and maybe even try to do a calculation. It's okay if it doesn't come out perfectly, but try and do a calculation to help you understand how that energy is moving from one thing to another. Like a subtraction is what I'm saying, a difference. But I want you to compare the two sides, the chemical reaction and the everything else, the surroundings. Okay. So if we just treat each one of these as like a single unit, each of these little marks, we start with 2 on this side and we end with 1. Okay. So that energy had to go somewhere, right? 1 unit of energy went somewhere. Where did it go? It went into the surroundings. So the surroundings started with 1 and ended with 2. So when I say a calculation, I mean a difference, right? 1 unit. Well, how do we describe, though, the fact that the system lost a unit and the surroundings gained a unit? So it's very important because I don't think we have any engineers in here. But engineers always want to look at it from the surroundings perspective. Like they're trying to get something out of a chemical reaction. Maybe they want to get the energy out, like if they're, producing energy. Or They always care what's coming out. As scientists, we care about the actual thing that's occurring. So if you've ever heard of this idea before of how to calculate a difference, make sure that it matches what I'm saying, because there are people that do it the opposite way around. Okay, so there's a lot of terminology here. The triangle symbol, Greek letter, capital, delta, means change. Okay, so you'll see a lot of change in energy or change in, we're going to use another term called enthalpy. It'll be an H, but you're going to see change a lot. Anytime you see change, it means a difference between a starting and ending. I always, always, always want you to calculate this final minus initial. Okay, so you're going to start with the ending value and subtract the starting value. Or another way to think of this would be like, if you're talking about a reaction, it would be products minus reactants. Okay, so if we apply that to the thing we just did, for the system, does everybody get what I mean when I say system and surroundings? I mean the system is the chemical reaction or the thing we care about, and the surroundings is everything else. Because if I have a butane lighter and the butane and the oxygen and then the products, the carbon dioxide and water, if that's the system, all of that heat's going to everything else in the universe, right? It may not spread that whole way. It's going to dissipate at some point, but it's going to everywhere else. So that's what we're talking about when we say the surroundings, is the other stuff. And maybe some of that heat goes to your hand, and maybe some of it you know goes to the air surrounding it, but eventually that heat is going to spread out, okay? So that's the surroundings. It's everything else. Okay, so for the system, for the chemical reaction, for the butane and whatever in this example, we're going to do final, which was 1, minus initial, which was 2, and we get a value for the change in energy of -1. Okay? When we do it for the surroundings, change in energy, final is 2, initial is 1, so it's a +1. It's very important that they're the same number. Again, energy cannot be created or destroyed, it's just transferred. So the fact that they're both 1 means that 1 unit of energy is transferred. The negative and positive are actually probably more important than the quantity itself. Okay? So the negative value here means that energy left the system, or it got smaller than what it started as. Okay? That energy left the system. The positive means that energy was absorbed or given to the surroundings. So when you have an energy exchange, it has to leave one thing and the other thing has to gain it. And the way we communicate that is with positives and negatives. So don't think of this as like a number line, positive and negative. Think of it as the positive and negative communicate the direction of the exchange of energy. The negative means it's leaving the system. The positive, because I'm talking about the change in energy of the system, so sometimes we'll write this as change in energy SYS, system, and we would write this as change in energy of SURR, surroundings. So the change in energy of the system is negative because that's where it's leaving. The change in energy of the surroundings is positive because that's what's taking that energy in. So at this point, you might be like, well, okay, but that was obvious from the picture. You're not going to have a picture every time, right? You're not going to have an energy diagram every time. So you have to be able to be given a number. Like if I say the change in energy of the chemical reaction, here's another terminology thing. We abbreviate reaction RXN, especially when we're doing stuff like this, so that we can specify we're talking about the change in energy of the reaction. It's nice to be able to write it shorter. So RXN is reaction. So if I say the change in energy of this chemical reaction is negative 695 kilojoules, you need to know that that means that 695 kilojoules of energy was given off, okay? Because that's the type of thing you're going to see. You're less likely to see a picture. You should actually be able to now turn that into a picture in your head and say, okay, if energy is given off, that means it started at a high energy and went to a low energy. You know, it doesn't really matter what the values were, but they differed by 695. So there's 695 units of difference between where it started and where it ended. This could be 795 and 100, right? Final 100 minus 795 initial, final minus initial would give you negative 695. That negative is telling you the direction. Similarly, if it was positive, so delta E of the reaction, let's say was 10 kilojoules, okay? The fact that I have that as a positive value is telling me that the reactants are lower in energy than the products by 10 units. So maybe this is like 800 and this is 810. So it went up in energy. Final minus initial, 810 minus 800 is positive 10. So that's why that value was positive. It went up in energy. You guys have that benefit of being the third class. This one took a while, but I think you're getting the best of it. Okay, so now that we've kind of like done an overview of where we are, let's treat it very formally. We're gonna have like some equations that tell us about a concept, okay? These are not, we might plug actual numbers into here, but mostly this is trying to explain a concept to us, these different equations, and there's gonna be some more down here, okay? All right, so there's actually two types of energy that play into energy, as we were talking before. So the energy I was talking about before is what's called internal energy, and that is like just self-contained in the thing, not based on like its gravity or anything like that. Just the chemicals themselves. They can have kinetic energy because they move around and vibrate. Okay, that's a very normal thing for atoms and molecules to be bumping around. If you guys remember, temperature in Kelvin is a measure of that kinetic energy. So when we say something's 200 Kelvin versus 300 Kelvin, that is literally, we're just saying the ones at 300 Kelvin, they're molecules that are moving faster. So that's one component of energy. Internal energy is the proper term. And then the second is potential energy. And that's probably the one that is going to make the most sense, I think, as we get into this. Because really, this comes from positives and negatives attracting. Okay? So when you form a bond, you get lower potential energy because you get those attractions, right? So chemical reactions are all about breaking up certain bonds and forming other bonds. And in that process, there can be a change in potential energy because you're adjusting what positive things are attracted to what negative things, and maybe some repulsion as well. So you've got all these positive and negative attractions, repulsions going on, and they might start a certain way when they're butane and oxygen, and then we rearrange those into CO2 and water, And in the end, in this particular reaction, we see that that's a lower potential energy in the products. That arrangement of how the positives and negatives are attracted is different. In a very simple example, just think of like if I have two oxygen atoms and I form an oxygen double bond, this is at a lower potential energy state because I just formed a bond, right? When I form bonds, I'm increasing those shared electrons like we talked about last unit. And so that is inevitably going to decrease the potential energy. Now, a chemical reaction is more complicated because you're breaking bonds at the same time as you're forming bonds. But it kind of overall, you want to know how that potential energy changes. And it really comes down to how the bonds are forming, how the interactions are happening. Okay, so those are the two types of energy that go into when we say E, we're talking about those two types of energy. Okay, we already talked about this idea of defining it as the change is final minus initial. Those other deltas shouldn't be there. That should be delta E equals E final, E initial. Okay? Okay. Now, how does this change happen? Like, how do we see it happening when we have a release of energy? Okay, so we said with the butane, energy is released. Well, the main way you see that happening is heat being given off, right? So that's number one. Then one of the ways that energy can be exchanged is through the exchange of heat. You can measure that as a change in temperature, but temperature and heat are not the same thing. So we'll talk about this on the beginning of Wednesday in more detail, but like if you add 10 joules of heat to a metal and you add 10 joules of heat to water, their temperature change is going to be different, okay? Because it depends on the substance itself, how it will absorb that heat. So heat is actually energy. Temperature is a measure of the movement of the molecules, which is certainly affected when energy is given, but it's not the same for every single chemical. So they are separate things. And then the second thing is something you're probably not as used to talking about as far as an energy exchange, but it's called work. So in physics, this is very straightforward because you can see it on a physical scale. So if I'm the system and I push on this chair, if I can scooch it. Okay, there. This is me applying a force. That's me doing work. Okay, I just released some of my energy and gave it to the chair. That friction was a little ridiculous, but I gave my energy to the chair by doing work on the chair. Okay, so that is one way that energy can be exchanged as well, is that you apply, the system might apply a force on the surroundings and give some of its energy to the chair. Now, we talked about sign of energy, positive and negative. And the signs apply to Q and W as well. So I'm going to skip us forward like 3 slides to this point. Okay, so same equation. Energy can be exchanged these 2 different ways. When we talk about heat, that's probably going to be the easiest for you to remember how the signs work because it's identical to how energy works. If I say energy is given off, I say that that's negative. Well, if heat is given off, like a butane lighter, that would mean heat is negative. Okay, so that would be in this far column over here. So something that loses energy should have a negative sign. If it's losing that energy as heat, that would also be negative. Q would be negative. Q is negative. The work is usually a little bit more difficult for people to understand. So when I pushed on the chair, we're pretending I'm the system and everything else is the surroundings. So if I push on the chair or I push on the table, okay, that doesn't work very well. I'm like, what else can I push on? I push on this chair. All of those are examples of me doing work. That would mean W is negative. Okay? Energy is still leaving the system, so the overall energy should be negative. It's just that in this case, it's leaving as work. So work would be negative. I was trying to think of an example of work being done on me. So somebody else would have to come push me. You guys would be the surroundings and I would be the system, okay? So energy being, it's not working anymore when it's me. We're going to have to switch to chemical reactions now. So let's do the negative side. Let's keep with the negative side for a chemical reaction, and then we'll switch to the positive side for a chemical reaction. Okay, so for a chemical reaction, the butane lighter was easy. It lost energy. It lost it as heat, so Q would be negative. In that case, energy would be negative. There's no work involved with the butane lighter, so we're going to switch the example. So an internal combustion engine, like in your car, little bit, it's the same type of reaction. It's a carbon-hydrogen compound, octane, with a little bit of oxygen, and there's a spark that initiates combustion, and it produces CO2 and water. It's the exact same thing as the butane lighter. The difference is the heat is just another byproduct. We don't actually care about the heat. What we care about is the gases, the CO2 and water that are created. So I should have had a picture. Ooh, you know what? I think I might have a picture. Yes. Huh. Okay, so this is a 4-cylinder engine, all right? And there's a little chamber here where the combustion of the gasoline is going on, okay? When that little droplet of liquid gasoline reacts with some oxygen, it produces CO2 and water, which at these temperatures is gas. The water, obviously the CO2, and the water is a gas. So you're in this confined space, and it's a very small amount, and then you make a gas that's big, and it actually pushes up on that piston. So the gas itself pushes on something. It's applying a force, and when all of these work together, those pistons moving rotates the axle, and that's what makes your car move. Okay? So the combustion of the gas, the creation of the gas, applies a force on the piston. So that's when a gas expands, or a gas is produced and therefore it expands and pushes on something. That's how a chemical reaction can do work. And that would be W is negative because it's pushing, it's giving its energy out as work. Okay, so back to this chart here. So that would be an example of work being negative. If you look up at the slide we were on before, I think it summarized that actually. Yeah, in chemistry, we see this as the expansion or contraction of a gas. So expansion is when work is negative because it pushes out on something. The opposite would be if you have a gas and something pushes in on it and compresses the gas. So if you think of like, I'm trying to think where you guys would have seen a compressed gas. Like helium balloons is what I was thinking of. You know those cylinders that they come in? That's a compressed gas. So the molecules generally are going to be pretty darn far apart, but they don't want to ship it that way. So they push the gas in and they compress it and it increases the pressure. That would be whoever's doing the confining of the gas. That's the surroundings doing work on the gas itself. That would be a positive W. So contraction, that should say, I don't know, contraction, compression. that would be when work is positive. Okay? And now we need an example of when Q is positive too. Okay, because that chart we had below, I'm not going to go back down there, but it was talking about when work equals negative and Q equals negative and then positives. So with Q being positive, that's just some reaction where you're going up in energy. A cold pack, so, you know, like an instant ice pack, so like a hand warmer, but the opposite. So if you crack the tablet that's in there and shake it up and then it gets cold, that is getting cold because it is taking the energy from your hands, from the surroundings, from the air, from your hands, and it's absorbing it to allow the chemical reaction to occur. So that would be going up in energy, meaning heat has to go in, and that would be Q is positive. Okay? This is very confusing to people sometimes because they're like, if heat's going in, shouldn't it feel hot? You don't ever feel the chemical reaction. You don't feel it. You don't measure it. You feel the consequences of it. So you are part of the surroundings. So if something feels hot to you, then the chemical reaction's emitting heat. You're feeling the consequences. You're the surroundings. You're getting that heat. If the chemical reaction is absorbing heat, it's going to be absorbing it from you, from the surroundings. And so you're going to feel cold because something's taking heat away from you. Okay? And this brings up our next kind of big point, which is this exchange between the system and the surroundings. Now, I want to hone in on the important part here, which is this. Okay? We've already talked about this a lot. And so I think we need to just hone in on the key point. This says that the change in energy of the system has to be the exact same value as the change in energy of the surroundings, just different signs, right? That's exactly what we did here. We showed that they were the same value, they were just different signs. And that's true of like a heating pack or an instant ice pack, right? It has a certain amount of energy that it needs to absorb to allow that chemical reaction to happen. It takes that exact amount of energy from the air, from your hands, from whatever's surrounding it for that reaction to occur. Okay? The reason why that's true is because the universe has to stay zero, no creating or destroying energy. And if all of the energy either goes to the system or the surroundings, that's what the second equation is telling us, either there's a change in the system and in the surroundings and they have to be equal to zero, then what we're saying is they have to be the same value, just opposite signs. And the reason why this is so important is because this is the thing we get to measure. We don't get to measure the system directly. We get to measure the surroundings. So when we measure the surroundings, all we then have to do is change the sign, and then we know what's happening to the chemical reaction. So in the experiment you guys did in Chem 1 with the styrofoam cup, and you measured the temperature change of the water, you were measuring the surroundings. If the temperature went up, that's how you knew, however much it went up by, you did a calculation, if you remember, using Q equals MC delta T. I'm not sure if this is coming back or not. No, not so much. That's okay. We're going to do it again. So when you did that, you measured how much heat was actually being given off. But the whole thing is that it was being given off, so because you could tell that it was positive for the surroundings, which meant it was negative for the system, okay? So the reason why this is important is because we're going to utilize the fact that we can measure the surroundings to tell us about the system. Okay, I feel like we need a breather for a second. Get a drink of water or something. Okay, 12 minutes. We got this. It's going to be good. Okay, quick note about energy units. There's quite a few different ones that we use. Joules or kilojoules is going to be the most frequent. So make sure that you can convert kilojoules to joules, right? This is just normal metric conversions, 1,000 joules per kilojoule. This table is interesting. I kind of like this one because it's like a 10 watt bulb. Now that we use LEDs, 10 watts is actually not a huge amount. I mean, that could be like a light bulb in a lamp could be 10 watts. That used to be like 100 watts or 150. So this gives you some sense of how much this is. So 3.6 times 10 to the fourth. So we're talking like 36 kilojoules would keep a light on for an hour. And chemical reactions are generally in the order of hundreds of kilojoules for like a mole of the substance. So like there's a decent amount of energy being given off there. We will use the unit calorie. This is not the same calories as in food. This is the calories in food. Do you see the difference? It's a big C versus a little c. That's very annoying. These ones are actually kilocalories, but I think they didn't want to scare people when they started publishing how many calories were in things. They didn't want to say kilo because then they'd be like, well, what's that? I don't know the metric system because I'm American, you know. So they just made a capital. They just didn't want to tell you that there were like 100,000 calories, this kind of calorie in an apple. They were like, we just want to be able to say there's 100 calories. So they use kilocalories. So just know that there's a difference in case you ever encounter that. We're never going to use kilowatt hours. As far as conversions on the exam equation sheet, there's two that you want to be aware of. So the calorie to joule conversion, and this is the little calorie. So calorie to joules is there. And remember, anytime you have things that are equal, you can set that up as a conversion factor. So 4.18 joules per 1 calorie. And then the other one we'll use when we do work calculations, because those involve a gas, is liter atmospheres. It's very weird, but that is an energy unit. When you do pressure times volume, that actually gives you an energy unit. And so that conversion is 101.3 joules per liter atmosphere. So again, you could just put that as a conversion factor. And we'll have to do this probably in class on Wednesday. But you can use that as a conversion factor, okay? So we're not going to do those right now. We'll do them when we need them, but just be aware those are the energy units we're going to see most frequently. Joules, calories, and liter atmospheres. And kilo, whatever, kilojoules. Probably not even kilocalories, but kilojoules for sure. So I'll just add that in there. 1,000 joules per kilojoule. So I have to like turn our math brains back on. I like brought calculators for the exam last weekend or last Friday, and then I was like, oh, we haven't even used calculators really. We haven't even like done any calculations. So we are definitely getting back to that though. Okay, back to the notes. So, I don't know how much we even need to talk about this because this is literally just a summary of what we've already said. So we'll treat it like that. We're just going to treat this as a summary. This is another chemical reaction. On the left-hand side, you have carbon and oxygen turning into CO2, okay? All they do on the right-hand side is they reverse it. So now they have CO2 turning into carbon and oxygen. The reason why they're doing this is because they want you to see a reaction where energy is released. So that's on the left-hand side. Energy released. And then they want you to see the same reaction but reversed so that you can see energy absorbed. Okay? And another way of thinking of absorbed is required. Like the reaction will not occur unless it can get that energy from somewhere. Okay? So what they're doing here is showing you all these different ways that we represent this. So we can represent it with an energy diagram, right? We can show that the reactants are higher in energy than the products. We can indicate that the delta E is negative. That's the one you're going to see given to you most of the time. When you look up a chemical reaction and you look up data about it, it's just going to tell you a value like negative 600, right? Positive 250. It's not going to tell you, it's not going to show you a picture, okay? And then knowing that if that's the system that's negative, the surroundings then must be positive, okay? Always knowing those are the reverse of each other. And then they also have these little diagrams showing you the flow of energy. So energy is going out of the system into the surroundings. Same thing here, out of the system into the surroundings. These are just different representations to like drill into you that this is what delta E negative, that's what that means or looks like. This is what delta E positive looks like. Okay? So really just a summary of what we've been talking about already. Okay. Last thing we're going to talk about today is not the bowling ball, what's that called? Pool? Billiards? Sounds fancy. All right, the last thing we're going to talk about is this weird idea that is very important for how we do these calculations. So internal energy that we've been talking about this whole time, kinetic energy plus potential energy, is what we call a state function. And what that means is that all we care about is where we started and where we ended. So like, for example, what the reactants were and what the products were. We don't care about how we got there. So like, if we had butane and oxygen and I don't even have a good example for this because you guys, we haven't talked about like intermediates and stuff. So I'm not going to do the chemical reaction analogy, or I'm not going to do the chemical reaction. I'm going to do an actual analogy, okay? So the analogy that's given here is we've got hikers going up a mountain. One is going straight up and the others are doing switchbacks, okay? 10,000 feet is ridiculous. No one's going to climb a 10,000 foot mountain all in one, but just go with it. So the state function would be similar to the elevation change. Okay, it does not matter which path the hikers take. They're all going to be having a 10,000 foot difference in elevation. Okay, that's how internal energy works. When we look at a calculation for internal energy, all we care about is like where we started and where we ended. And the value isn't going to change whether we hike straight up the mountain or whether we crisscrossed, okay? It's still going to be 10,000 feet. Internal energy works like that. There's another one called enthalpy that's going to become really important. It's also a state function. And the reason why this is so important to know is because it allows us to do some easy calculations. If we don't care what happens in the middle, like we only care about the initial and final states, we can do a ton of weird, funky calculations that only work because these quantities are state functions. Heat and work are not actually state functions. So the two of them added together that equal energy. Energy is a state function, internal energy, but heat and work are not. And so it affects how we're able to do calculations. So the example there is heat and work are like the hikers. So the path that they take is going to affect the mileage. Like you can take the 5 miles straight up, or you can take the 12 miles back and forth. So that would be equivalent to heat and work. The mileage would be affected based on the path. The other way we say this is that we talk about state functions. Think state means like just dependent on final and initial state. That's why it's called that. The other way we talk about this is path independent. Like it doesn't matter the path you take, it only matters where you start and where you finish. Okay? So internal energy and this quantity we'll talk about on Friday called enthalpy, those are state functions. Heat and work are not. It very much depends on the path you take, and that's going to make it more complicated. Okay? All right, we will end there. I think that went okay.